Magnetic field along the axis of circular coil carrying current. Aim: to study the variation of magnetic field intensity with the distance along the axis of a circular coil carrying current, and to verify the value of horizontal component of Earth's magnetic field B0. Apparatus: circular coil, compass box, ammeter, rheostat, commutator, cell, key, connection wires. Theory: a current-carrying wire generates a magnetic field. According to Biot-Savart's law, the magnetic field dB at a point due to an element of a conductor carrying current is directly proportional to the strength of the current I, directly proportional to the length of the element dl, directly proportional to the sine of the angle theta between the element and the line joining the element to the point, and inversely proportional to the square of the distance r between the element and the point. That is, dB is equal to mu0 by 4 pi into I dl sine theta, the whole divided by r square. By Biot-Savart's law, the total magnetic field at a point which is at a distance x away from the axis of a circular coil of radius r having n turns is given by B is equal to mu0 Ni divided by 2 into r square divided by x square plus r square the whole raised to 3 by 2, where mu0 is equal to 4 pi into 10 raised to minus 7 Henry per meter is the absolute permeability of free space, where n is the number of turns of the coil, I is the current flowing through the coil, r is the radius of the coil, and x is the distance of the point from the center of the coil. The magnetic field with the distance x along the axis of the circular coil carrying current varies as shown. If you arrange the plane of the coil parallel to the horizontal component of Earth's magnetic field B0, then from the tangent law we can write B is equal to B0 tan theta, where theta is the deflection of the magnetic needle from B0 at the point P, and B0 is equal to 3.5 into 10 raised to minus 5 Tesla. Procedure: first we have to adjust the apparatus in the magnetic meridian. This can be done as follows. Place a compass box on the slider at the center of the coil, that is x is equal to 0. Rotate the compass box till its 90-90 reading become parallel to the plane of the circular coil. By rotating the whole apparatus in the horizontal plane, make the aluminum pointer to read 00. Now, the apparatus is in the magnetic meridian and the coil, needle and its image all lie in the same vertical plane. To find the magnetic field at different points, set up the electrical connections as follows. The negative terminal of the cell, E, is connected to one end of the rheostat R through a key K. The other end of the rheostat is connected to the terminal 3 of the commutator. The positive terminal of the cell is connected to the terminal 1 of the commutator through an ammeter. The circular coil is connected to the 2 and 4 terminal of the commutator. Place the compass box at the center of the coil. Using the rheostat, adjust the current such that the deflection of the aluminum pointer is between 30 degree and 60 degree. Note the reading at both the ends of the pointer. Reverse the direction of the current using commutator and again note the deflection. Then calculate the mean deflection theta at x is equal to 0. Then place the compass box at another distance, say 5 cm, on the right side from the center of the coil. Note the deflection of the aluminum pointer for direct current and reverse current. Calculate the mean deflection theta. Repeat the same procedure by placing the compass box at different distances on both sides from the center of the coil. Note the mean deflection at each point and calculate the corresponding magnetic field B using the equation B is equal to mu0 Ni divided by 2 into r square the whole divided by x square plus r square the whole raised to 3 by 2. By knowing the theta values and B values at different points, we can calculate the horizontal intensity of Earth's magnetic field B0 using the equation B0 is equal to B the whole divided by tan theta, which is a constant. The experiment can be repeated for different number of turns of the coil and for different currents. Applications. In the construction of stellarators. A stellarator is a toroidal magnetic confinement device that is characterized by having magnetic surfaces created entirely from external magnets. Traditionally used for fusion research, stellarators possess unique properties that make them attractive as charged particle traps. The principle of circular coil is applicable in the working of loop antennas.